I mean, okay, I'm gonna do that update again. Oh wait, 1, 2, 4, 5. No, we're missing a few. Okay, so right, I am entertaining a slight syllabus change, which is that I will change the order of these 2 weeks, and I will remove this requirement and this requirement. This is this week. So that's why we're not changing that. You know what Quarto web pages look like because you've seen them. The examples that I compiled for the rubric day, those were Quarto compiled. You don't know how to get them online yet, so I'm going to teach that over time. Okay. Does anyone have anything they want to talk about before I introduce SymPy? Okay, here's how confused I am by them. Look at this. Even on my slides, I'm referring to it both ways. That's crazy. Did I do that the previous week too? Okay, no, these ones are both right. Some of you probably have experienced this. I cannot perceive the 2 letters between the S and the P. They don't exist to me. So they're not there mentally. And so, however I look at this, it's like really hard for me to differentiate these 2 things. And separately, and this doesn't help, they're both used to do calculations. Now, it's totally different types of calculations, right? But I'm like, oh, the thing in Python that starts with S, ends with py, and is used to do calculations, right? So that's what we're going to be dealing with. I did not name either of these. I suspect they didn't know about each other when they were getting named. Terminal. Have anything in here? Oh, there's lots of stuff in here. Okay, cool. So, SymPy. Why SciPy? We already did why SciPy last week. This week is why SymPy. Again, I can't do it. Okay. What is SymPy? It is a Python library for this kind of thing I'd never heard of actually. It's symbolic mathematics. Now, they just mean algebra. But I think it's easy for us to understand that you can ask a computer to add 2 numbers together or to ask it for a square root. It might be non-obvious how you ask a computer to solve a system of linear equations. And it might also be a lot more annoying to solve a system of linear equations yourself, especially when the computer can still do that. The difficulty that is incurred on you now and why I push this later in the semester is there's just more computer stuff going on when we start asking it to do algebra, because we have to sort of keep track of the difference between the variables that exist in our programming language and the variables that exist in our equations, right? So there's kind of, I would argue, no graceful way to do this. Oh my gosh, excuse me. I'm in shambles. Okay. I wonder what I'm allergic to. There's nothing alive out there. Okay. Anyways. Why am I teaching you symbolic Python? Symbolic Python is actually one of the reasons to teach Python at all. I suspect at various points in your academic career you will see brutal differential equations that you haven't reviewed for a while, and it could take you days to figure them out. This has happened to me. I've seen systems of equations that's just I have to look through 3 different textbooks to figure out how to solve this equation. And it's not I can't do it, right? It's just why am I going to spend a week solving this one equation, right? So over time, I sort of built up to learning SymPy instead. I just learned SymPy in the last year or 2. I actually started learning it when I was planning to teaching this class. I'm using it in my other classes now. So it became useful quite quickly once I knew it. That sort of convinced me that it might be a useful thing to know. And then some of the science faculty here also use it. So SymPy has an advantage over other computational mathematical systems, and the most famous one I believe is called SageMath, which is that they didn't write their own programming language. A lot of these symbolic math systems, and SageMath is famous and Wolfram is famous. I don't know if you have all seen this. I'm going to show you this now. It's unrelated to course content. But I don't know if you know about Wolfram Alpha. Do you know about Wolfram Alpha?
Yeah.
Okay, so Wolfram Alpha is awesome, right? And also it's the good version is not free, right? So the good version of SymPy runs on your computer. So it's sort of like you have full-powered Wolfram Alpha for free, which made it very hard for me to understand why I was ever stressed out about running out of power on Wolfram Alpha. But I didn't know about SymPy at that time. It's also fast. Python was not fast when SymPy started being created. It became fast over time, and so this is just a free bonus that now SymPy, for the most part, is quite high performance. Yes. Sorry, I was saying Wolfram, I meant Mathematica. So the competitors are Sage Math and Mathematica. So Wolfram Alpha is fine. I have been citing my sources all term, and so far, every time this term, when I've introduced one of these libraries, I've done a citation to a URL. This is a little bit different. The citation for SymPy is this was actually published as a research paper, which is pretty cool, which means it has a DOI. Do you know what DOIs are? It's a digital object identifier, and that's one of the ways that peer-reviewed publications are documented and shared. So here is the academic research publication that is not that old, 2017, kind of recent cosmologically, right? And you can read this if you want. I don't know that it will be particularly interesting to you. It wasn't necessarily particularly interesting to me, but you can follow along with examples. This is also an example of there being large amounts of text with embedded code snippets. So if some of you are interested in seeing how people speak in prose about code they are writing, this is probably like one of the highest quality examples that exists. It contains, for example, tables, and I don't think this one has graphics in it necessarily, but it does have equations, and I am going to show you how to display equations today as well, or this week. So maybe this is interesting for you to click through. It is quite lengthy. You are not responsible for knowing all of the content in this. But it is probably something that is helpful to look at. I'm going to show you how I found that again. So this is the citation. You can, of course, just throw this into Google or the search engine of your choice. But when I'm looking for these, I look for the URL. I take the URL, I copy it, I paste it, and it takes me directly. Well, notice the URL changes when I put it in. That's because the digital object identifiers is actually a way of looking up papers. There's actually a query that goes out to the digital object identifier people, and it gives me back the location of the paper. What this should mean is that if this website crashes someday, that same link will still give you access to wherever this paper will live now. So it could move somewhere else, and I don't know that it was originally published here. Okay, so that is SymPy. In order to get SymPy working on our own personal devices so that we never have to pay Wolfram to use their Mathematica, we are going to Python 3 pip install SymPy. And whenever we do this, we always point out some system differences. So you might have to just say Python. And depending on if you're on Mac or something, you might have to do like break system packages or something like that.
I like breaking packages.
They don't seem to break that often. So
I have to break them every time I install stuff.
you have to be allowed to break them. But if you did break them, your computer would stop working. So
Great.
you can trust me. I would never break your computer. We can verify that SymPy is working in the typical manners. We can use -c to run something directly at command line. We can import SymPy, and then we can say something like, I don't know, print SymPy. And that will tell us if we have a SymPy there. I'm going to make this full screen so you can see it. So that's just all on one line. And I'm able to have SymPy. I don't know if there's, for example, a version in here. But I have 112, which I think is the same version as my SciPy. Did I make that up? Did I check the version of SymPy last time by accident?
Yeah.
That's great. Oh no, they're just close. I think probably a lot of these versions are attached to the NumPy version, but I've been wrong before. So these things are all on version 1. There's never sort of been a version 2 of them. But anyways, this tells me that I have SymPy and that my install was successful. I'm going to get it out of full screen, and so those things just don't fit on one screen. Okay, so let's show an example of, okay, sorry, my brain is not as big and juicy as I want it to be. It's full of cerebrospinal fluid, but not ever quite enough, right? Or perhaps too much. I think that when there's too much, you have a swollen brain. That's bad, right?
Yeah.
Any health scientists? Okay.
Yeah, it's bad and can cause serious brain damage.
Okay, so I probably don't have that problem.
It's that.
I think what I have is like a lack of focus or something, which has nothing to do with cerebrospinal fluid. Okay. It's nice having real scientists around because you can just ask them questions. Like, is there fluid in my brain? And they're like, yes. Why are you asking? Okay, let's go ahead and get Python going. I want to motivate why you might care about this, which is that sometimes in the sciences, you might work with big numbers and you might want to do math on big numbers that is correct. So you might say, work with 10 to the 100th, and you might work with 10 to the 100th plus 47, right? These two numbers are not the same as each other. And I think that would seem obvious to us that they're not the same as each other. There's only like one sort of little tiny problem here, which is that you would expect this to still be the case if you put 10.0 there. And it's not. And usually in the sciences, we are working with numbers that have that are not integers, right? So not a whole number representation. So the number of seconds that it takes something to do, the number of grams that something weighs. So I think I tried to weigh out 32 grams of something yesterday, and it was impossible. Like, I kept getting 32.1, like, no matter what I did. And so frequently we were going to say things like, oh, maybe we're using scientific notation, but I have my 32.1 grams, and then I have my 32.1 grams. And then this equation, which this should be true, right? But I can add some, like, pretty large numbers to that, and it still comes back saying that those numbers are the same as each other, and they're really not. Those two differ by more than a quadrillion. I think I typed in there. So those numbers are not like necessarily particularly close to each other. They're just close relatively. The same thing is also true with fractions. I'm somewhat accustomed to 1 divided by 7 times 7 equaling 1. And that's really nice. But it should also be the case if I throw some zeros on the end of that 7, and I think I'll do 6, because it's easy to count. 1, 2, 3, 4, 5, 6. 2, 3, 4, 5, 6. I would have expected that to still be 1, and it's not. So what's going on here? Under the hood, deep within the folds of the brain of my computer, it's doing rounding. And sometimes that doesn't matter, and sometimes it matters a lot. The time, to my knowledge, it matters a lot is when you're doing calculations for like human spaceflight, which is when I was doing this and it mattered. You could not make errors of more than, of fewer than 6 nines of precision. So if you didn't have the 6 digits in a row without any rounding, you would get a problem. And this example right here shows that with 6 zeros, I'm able to get the problem. So that the computer does not have high enough precision for human spaceflight. It can only go to 5 digits. That's not enough for all applications, so this is not good enough for NASA. What's going on here? You are under no obligation to care about this slide. But what is happening under the hood is in the early days of scientific computation, which I believe was in the 80s, computers were not that big. They did not have that much storage in them, and there was not a graceful way to store highly precise numbers. They packed big numbers into small amounts of information, and it caused there to not be enough information to tell numbers that were close to each other apart from each other. This is called the floating point standard, and sometimes when we've seen things in NumPy that pop up and say int or float, this is what it's referring to. The floats is a older scientific computing technology that is insufficiently precise for some modern applications. Every time we have used non-integer numbers so far this term, we have been using floating points, and those are not always good enough, so I'm going to teach you the alternative. IEEE 754 is the standard written in the 80s that describes how all computers in the universe are going to use the same floating point numbers, which is why if you type this into Python on your computer, you should get the same results I do. This was not necessarily guaranteed before the 80s, and so in addition to the math being wrong, it was also inconsistent. Now it is consistently wrong. This is a significant improvement. So, what are we going to do with this information? We can take a look and learn something about the floating point numbers on our system by importing sys. Sys is just a name of one of these other modules or packages or something that exists in Python, and we can examine our computer using it. And we can ask the system for its float info. I have never looked at this in my life, but what this is a large amount of descriptions of how accurate or how inaccurate my numbers might be. For example, my computer cannot store numbers larger than this. It has to regard them as infinity. It cannot raise numbers to greater than this power, and so on. And I think this is a power of 2 and this is a power of 10. It can't do more than 15 digits. This epsilon this is how it cannot measure numbers that are closer to each other than this. So if I put in, oops, that's not what I meant to do. Let's see. Control-Shift-C. C times 10 to the negative 16. And if I can I put a 4 there? Okay. Oh, this is fun. I don't know, you can add these to each other or something. Times 10 to the negative 16. And you will begin getting precision loss at this difference from each other. And I think the way we do that is we say 1 plus this much. Control-Shift-C. Nope. Okay. There we go. So if I try and add that much to 1, I lose significant amounts of information. And I cannot tell these values apart. So if I put a 3 here, or a 6 here, the numbers cannot be differentiated, and they appear to be equal to my computer. Is this interesting to us? Only if the math stops working for you. So you break out SymPy when your numbers start looking wrong. And usually when they look wrong is when you add two things together and you get a different result than you expect. So this is important. It was important for science and engineering, and we needed something better. We can look at this a little bit also through the lens of history. So how many of you have heard of the, for example, Nintendo 64? So the Nintendo 64 had 64 bits of precision. It replaced earlier devices that had fewer bits of precision. Some of you may have heard of 8-bit sound, right? Yes. So there was a progression from 8 to 64 bits that occurred over time. The floating point standard was set when 32 bits were the most common, but it also supports 64 bits. We can look at this example using NumPy. So I'm going to import NumPy as NP, and I can look at a 32-bit float, so older than the Nintendo 64. And we might think of the Nintendo 64 as relatively old, and I think that is true, but it is also not older than the moon landing, right? So there was science going on before the Nintendo 64 that had extremely precise measurements. There are, for example, hydroelectric dams that are older than the Nintendo 64, and it was very important that those hydroelectric dams not fail because I live downstream of one of them and I like being alive, right? So I'm highly motivated for my numbers to be accurate. Separately, we can also look at 64-bit floating point numbers, and we can see we get considerable additional precision over the 32-bit float. These are not twice as big, they are twice as accurate, which means significant additional numbers of decimals, right? So I can express all of these additional numbers, which is many times more numbers than are expressible in 32. In fact, it's I can express that many times more numbers because I have an additional 32 bits of precision. So these are floats. I should share this. The default float type in Python, because Python is newer than Nintendo 64, is the 64-bit float. There are a few other things we can look at, and these are sort of some of the special values that are part of the floating point standard. So when we looked at, what did I press? Something I didn't mean to. Is this dot, was it float info? I mentioned we can't really deal with numbers bigger than this. So I think if I say 10.0 to the 309, that number is simply too large. But I think I can also do this with NumPy. So I can say x equals np.float 64 10.0. Okay? And I can look at that value, and then I can raise that to the 309. And I get a different error. Specifically, what error do I get when I switch back over to NumPy? I go from not seeing any value. I get an overflow error, numerical result out of range. I get instead, in NumPy, because I'm allowed to do this, I get a warning, and then I also get back infinity. So this can be a little bit interesting. Y is equal to infinity. I can look at the type of infinity, and it is a NumPy float 64. And I think if I did, for example, x to the 308, that is allowed. So precisely at 309, my numbers become too large to deal with. Okay? There are other values that are not necessarily allowed. One of them is you're probably familiar with what square roots are. I can take the square root of 25. It is, of course, against the law to take the square root of -1. But if I want to store the result of the square root of -1, I can throw that in a y value. And that is non, which stands for not a number. So there is such thing as floating point non. And I think you can just type that in by saying np.non or an np.infinity, and you can have access to these values. This, of course, immediately suggests what happens if you multiply infinity times 0, and you get in trouble. May also be worthwhile to divide infinity by infinity. That is also necessarily 0, 1, and infinity, so it must be not a number as well. So, look out for a few things. When you add numbers together, they might gain or lose numerical values. I would have expected a computer could add 0.1 to 0.2. It cannot. I would have expected that if I add 0.1 to something 100,000 times, that would be the same as adding, or same as multiplying it by 100,000s, but we can look at this difference. Let's see, paste. Ooh, that's not going to work. I have to split this. Okay, so for I in range, I think that's 10,000. 1, 2, 3, 1, 2, 3. Total plus equal 0.1. There's the total. And I would have expected that to be the same as 10,000 times 0.1. Because adding something 100,000 times or 1,000,000 times, I think that's 1,000,000. 1 followed by 6 zeros is 1,000,000, right?
Yeah.
So if I have 1,000,000 tenths, I expect that to be exactly 100,000. And sometimes it is and sometimes it's not. So it depends on things, whether it is or not. And then you also want to be relatively careful about setting two things equal to each other. So for example, I would assume that 1 plus 2 divided by 10 is equal to 1 divided by 10 plus 2 divided by 10. And it is not. So that is a bit odd. And then the last thing is if numbers are too close to each other, they might turn into 0 when you subtract them. I'm just going to copy this because I don't want to type in however many zeros that is. I counted those zeros to figure out how many it was, right? And it's a lot. But the computer can't tell these are different, and when I go to print them out, they look the same as well. So this can be frustrating. So what are we going to do instead? We're going to use symbolic computation. I'm going to follow components of a tutorial, and this is going to solve the problem of your computer not being able to do math. Okay, so I want to read this exact quote to you so you can hear from them, right? Symbolic computation deals with the computation of mathematical objects symbolically. Sounds a little redundant, but the introduction of this term mathematical objects is interesting. The mathematical objects are not represented exactly or numerically, right? They are represented exactly as a symbol. And so there is no loss of precision at all until you ask to turn the symbols into numbers, and then you can get as much precision as you want, but you might have to ask for more. So the mathematical expressions with unevaluated variables are left in symbolic form, so we can now work with algebra directly in the computer system. So let's look quickly at non-symbolic computation. And what I'm going to do is I'm going to look at my beloved 3, 4, 5 triangle. Do we all love the 3, 4, 5 triangle? Truly excellent triangle, right? 30, 60, 90, I believe. Did I make that up? Yeah. Just like one of the triangles of all time, right? My next favorite one is the 6, 8, 10, right? So let's go ahead and let's calculate the length of the hypotenuse of a 3, 4, 5 triangle. I'll calculate the square root, and I'll take a square of 3. So this is 3 squared, and you can denote this either way. I don't care how you do your squares. You can also do, we can even just do both in the same thing. So what this will give me is this will give me the length of the hypotenuse of a 3, 4, 5 triangle. And wait, what am I doing? Oh, sorry, I put a comma there instead of a plus. I don't know why I did that.
Wouldn't this be a 3? The 2? Never mind.
So that is 3 squared. 3 to the power 2. Yeah. So if we put a 3 here, everything explodes. But if we put a single multiply, it's fine. Something that I would like to impress the importance upon to you in general, but just in response to this question, is the computer will do exactly what you say. And it might look like it is doing something other than you thought you said, right? But the difference between 1 and 2 asterisks is important. And there's other examples too, so the difference between single and double quotes also matter. So 1 or 2 of things. These are different results, right? But that is allowed if I close the quote. And in fact, I can close quotes inside, but I cannot mix, right? So all of these things are always going on in the computer, and exactly what you put into the computer is what will be evaluated. This is important because every once in a while someone gets hired to design a bridge, and the bridge falls down because they did a square root incorrectly. That's my understanding of the story from this picture. I don't know if that's true because I'm not actually a civil engineer, but I tried to look up a case where it matters if you do a square root incorrectly, and I guess it was this one. I think what happened is they did a slight rounding error on a square root and then multiplied it by like 1,000,000 or something, so it had a very large error. One of these things can happen is like, oh, say for some reason, there's no real reason you shouldn't be able to design a bridge in millimeters, right? But it causes all of the numbers to be much larger, so you can inflate errors very quickly, right? So anyways, look out for this stuff. What you should do instead, and let's take a look at an example here. We're going to look at NP square root of a 2, 4 triangle, SQRT. 2 times 2 plus 4 times 4. So say we're trying to get that value, and we're trying to calculate what that value is exactly instead of approximately. This is the same as, I think, the square root of 20, right? Because that's 4 plus 16. But maybe we can do a little better than that. And we are going to do a little better than that using SymPy. So at this point, I'm going to begin using SymPy to solve the problem I've created. I'm going to import SymPy. Similarly to SciPy, and again, this did not help my confusion referring to them ambiguously as each other. my impression is it's dramatically less common to say import SymPy as SP, which is what I would expect from NumPy. And I think a lot of this actually has to do with the fact that the same people are using SymPy and SciPy, and they would call both of them SP. So we're just going to call this thing SymPy. We're not going to simplify its name. And I think that's not going to be too bad because we can take some look at what's going on here. Once I'm in SymPy, I can create variables, but I have to create variables intentionally. And the way I'm going to do that is I'm going to give a variable a name with a string. And then I'm going to say SymPy.symbols of that string. And SymPy is going to give me back a variable. So how do I do this? I can say SymPy.symbols x. And I'm going to ask to have the symbolic value x. So it is going to look like an x when I show it up, but it is going to be a different type of thing. And this has created my symbolic value x. Now, what I want to point out is this symbol, which turns into x here, is different than Python x. Because Python x currently has a numerical value, and if I add 7 to Python x, it's going to perform a literal computation. So in order to create a Python variable that has the same name as my SymPy variable, I'm going to use single equals assignment to assign Python x, which looks like this, to SymPy, symbolic x. And when I do that, I will get x back when I ask the value of x. And that means if I ask for x plus 7 or x squared, I will get back the symbolic value that is represented. I can create another symbolic value, SymPy.symbols y. Oh, I didn't close my quotes. And then I can say x plus y, I can say x times y, I can say I can say x squared plus 2xy plus y squared. If I have a symbolic equation, a quadratic equation, right? And I think that is the same thing as x plus y squared, but I don't really remember. But we can figure out how to do that. So let's start by taking the distance example again. And we can say, for example, distance equals SymPy square root of x plus y. And then we can take a look at distance, and it is represented symbolically as follows. You'll notice on the slides this is showing up a little bit differently. That is teasing a little bit 1 week ahead that when you start running this stuff in Quarto instead of in the terminal, it is going to look nicer. Just be advised that that is coming down the pipeline. We can do arithmetic on this distance, and it will preserve the distances. We can perform both literal arithmetic with 2 and symbolic arithmetic with z. SymPy.symbols. I will create a new symbol named z, and then I can say z equals square root, z times dist. And that will give me z plus the square root of x plus y. I can make many symbols at once if I want to, and I think you will often want to do this. And I can do this with comma separating variable names. So I can say a comma, oh, what did I do? I did something terrible. Okay. A comma b comma c equals SymPy.symbols a space b space c. And then I can look at a, b, and c. Are they equal to each other? Not yet, but they could be. And we can also look at how SymPy, so note this is not NumPy, right? So we also have NumPy square root of 20. We don't have a built-in square root of 20, but we can raise 20 to the 0.5 power, which gives us a similar value. We can also ask for the symbolic square root of 20. And what we will get instead of a numerical answer, well, I don't know, you could argue this is numeric. We will get a precise answer that contains no rounding, which 20 is equal to 2 times the square root of 5. 2 times the square root np dot square root of 5. And we can see that that is equal to the square root of 20. Oh, there we go. So we can get extremely precise results back from SymPy using these values. We can do most of the operations that we would normally do on any form of arithmetic using SymPy, and we can also get really, really high degrees of precision. So for example, I just showed this, but come on. Square root np dot square root of 20. This is relatively accurate, but we can also say, let's see, I can say SymPy dot pi dot evaluate as a float up to 100 bits of, or 100 digits. And I can get very precise answers. And that is just by looking at SymPy.pi, which is a built-in value in SymPy I have. I can look at other things. So I can look at root of 20, which is equal to SymPy.square root of 20. And I can say root of 20. This looks the same as SymPy.pi. It has the same type as SymPy.pi. Type of root of 20. So these are both core SymPy.core values, right? And then I can say root of 20 dot eval f. How many digits would you like to see?
50.
There you go.
Yay!
And then again, we'll just compare that to baseline. Dramatically higher accuracy, right? We can also perform variable substitutions. So we may recall that we had a distance calculation earlier. And maybe that's not a true distance calculation. Maybe we want to say distance equals SymPy. And I think I can actually just say np square root too. X squared plus y squared. Let's see. SymPy. There we go. So here's the distance. It's the square root of x squared plus y squared. What can I do with this? Well, given distance, I can substitute in a value for x or y. So here I'm going to substitute in, we'll consider the example of the 3, 4, 5 triangle, where we set the y to be equal to 4. Let's see, what did I do? Sorry, I didn't put in enough. I have to say that I want to substitute it in for y. So I'm going to substitute y equals 4. And that is going to say the square root x squared plus 16. This probably makes sense. And we can do the same thing with, for example, x. And if we want to, we can do more than one substitution. And then we will get a numerical result back because we placed in all of the values. Something I want to point out that is potentially interesting to you, that is integer 5. And previously, when we were calculating np square root of 3 squared plus 4 squared, we were getting back non-integer 5, so we have improved our accuracy in this case already. We can also substitute more complex arithmetic expressions. So we can look at distance again, and perhaps we want to substitute for y. I'm going to say a times a plus b times b. Pow object is not callable. Right, dist dot subs y a times a plus b times b. And this will do all of the calculations you want it to do and keep track of it. And then I can, for example, substitute a for 7 or whatever you want to do, right? Just completely completely reasonable. Is this super easy to look at? No, I'm not claiming it is. I'm claiming this is easier than teaching yourself ordinary differential equations. We can also type in expressions as strings. So I'm going to type in my string expression. No, I'm not. I'm going to press hotkeys by accident. String expression. So I think let's do, I don't know, 9x squared plus 6x plus 3. I'm going to put that in quotes. And I'm going to set it equal to the string value. So here's my string expression where I tried to type in an equation. I'm going to use SymPy.simplify, which I think is a function older than the term simp, so that's probably why it's named that. And I can simp the stir expression, and it will give me back. I think this is kind of cool. It gives me back what the expression is. I can save that as an expression, and I can, let's look at the expression, and then I can also just substitute something for x. Oop. Oh, subs. It's subs. Thank you. Good catch. Thank you. So, I mean, maybe that's a good way to do things. It depends on how much you like doing algebra. I think it would have taken me a long time to do that mentally, and it would have taken me a certain amount of time to get out a calculator to do it as well. We can also, and this is, I think, where it begins getting really useful. We can take a symbolic function and we can turn it into a Python function. So instead of having vectorized like we did with NumPy, where we took a regular expression and turned it into a vectorized expression, we're going to have something called lambdafy, which is just named after the lambda character in Greek. And so we can take a SymPy expression and turn it into a Python function. SymPy expressions contain variables, so the Python function is going to expect variables, and then it will compute a result. So we can do that here. We can say f, and I'm just going to name the function f because what else would I name it, is going to be sympy.lambdafy. How do you spell it? I'm going to lambdafy it. I have to say which variable I care about, so I'm going to do it with respect to the variable x, and I'm going to do that of the expression. I here am specifying I'm going to use the SymPy engine for math. You don't have to do that. It leads to better accuracy. That was a bit slow. I don't know how slow that will feel to you, but I was able to notice that that took a certain amount of time. It's not necessarily an easy thing for a computer to do, but it's much easier for the computer than it is for you. And from there, we can calculate f of 4, f of 3, f of 2, and f of 1. I think I said it was this expression, so that is plus 3. So I expect when I put a 0 in there for x, this term will go to 0, this term will go to 0, and I will be left with 3. So if I think I put 0 in here, it'll be equal to 3, and it is. So that is the Python expression created by typing in a string, which is, there was a lot of steps to that. Again, I don't necessarily think this is the easiest thing in the world to do, but I think it might be easier than doing algebra yourself. That's the pitch here. You can also use this to start graphing things, basically. So you can say, you can vectorize that expression over a NumPy array. And once you can do this, you can start looking at some other things. Like, for example, oh yeah, you're supposed to do this. Here, sorry, I'll do this again. Oh no. Oh, I'm getting the enter. I'll just type it. F equals sympy.lambdify x expression Skippy. And that's going to be pretty much the same. Same values. From here, you can now make plots, which this could be kind of interesting. So what am I going to do? I'm going to import the the number of times I start typing after clicking on this screen, and then it just does stuff in the browser. Okay, so import matplotlib.pyplot as plt. Let's do some calculations.
Yay.
I'm going to take some x's values, which is going to be a linear space from -10 to 10. I did 5 on the other side of the screen. That's fine, doesn't matter. Is that going to work? There it is. So that's like a bunch of values. I'm going to plot x's and f of x's. I created the plot. Save fig. We're going to call it SymPy. I'm not going to put a quote in there. .png. I'm going to import OS, and I'm going to say os.system. Open. Some of you are going to say start. sympin.png. Ooh, did it not work? Oh, no, I spelled it wrong. I said Sympian. And that's a parabola. Who loves parabolas? Oh, you don't love parabolas?
I don't like parabolas.
Do you like something more than parabolas?
A quadrattle. What's it called? I forget, bro.
A hyperbola?
Quadratic. Thank you.
A quadratic?
Mhm.
This is also quadratic.
Oh.
You
I'm
mean
sorry.
like log?
Mm.
Exponential?
Do you do the shape like with your hands? I might be able
Yeah,
to.
exponential maybe?
That one? That's
No,
what.
no, that's that one.
Logarithm?
Cubic.
Oh, periodic.
Oh, okay. We can try a few other things, right?
So, like tangent graph. Those ones are cool.
What is it?
Tangent. Oh, yeah. You know what I'm talking
Hey,
about?
we want the tangent?
So tangent.
Yeah, it's called periodic.
This probably works.
It's like the fracking enough down the cotangent.
Did I get it? Okay, so I added the tangent to it. It's not looking particularly graceful.
No.
Looks like a weird heartbeat.
Look, yeah.
Yeah.
Does
Yeah.
not look
That's really
period.
unhealthy.
I mean, it is
Very
very
I don't like
I mean, this is what it should be, right? That seems fine. Relatively small values. Sorry?
Is it scalable?
It's quite compressed because we already have the parabola on there.
Oh, yeah.
Clear figure matplotlib pyplot. plt.claw. Okay. We'll add that. Say fig. Is that better? I kind of feel like that's what it's supposed to look like, right? This is at oh, maybe we want it smoother?
Yeah.
And then I don't really like a tangent. I don't like tangent. I like sine or cosine.
Okay, we'll do sine or cosine.
No, I'm just saying, you didn't have to do it.
No, I'm being bullied. Did I actually get it?
You didn't save it.
All right, save it. Who's responsible for saving these things?
Beats us.
Oh, I like those.
Not tangent.
I don't like the tangent as much.
Tangent is like it.
I don't think.
You're a tangent hater?
Yeah, I'm a tangent hater.
Okay. We'll claw them off.
Oops.
I'm just doing the things I did again. That's why I'm just pressing up arrow. I think I have to save the fig, and I got to pop it open. Since my computer's not that hot, I refer to this as cracking open a cold one. Yeah, that's a lot of people don't know that trick.
Right.
So cool. But that's
Ooh,
cool.
I like that.
Yeah, see, and a little bit of. So maybe we could use a slightly higher resolution, right? So, what is the length of x's? Not that high, right? So instead, we can do x's equals np.linspace. I think we did -10, 100, and we do like 1,000. And I'm gonna put this on the same axis so we can see how much smoother it gets. Pop it open. Please be open.
does that mean from the range -10 to 100, you're having 1,000?
Well, let's look at it. I'm not sure what it is. So it's just many more values, right?
Yeah.
And so, not super easy to see, but one of these is like much smoother,
Yeah, the green one.
right? So yeah, you can always make your plots smoother if you want by doing that. Okay. Takeaways from this: you now know how to plot functions.
Yay. Mm.
Yay!
Go back to our piecewise.
Yeah, we can, right?
What the heck?
So here's an example of something I never remember. You all seem to know trigonometry, which I don't. So apparently, the sine of x squared plus the cosine of x squared is always 1.
Yeah.
I didn't know that. I assumed you'd have to like decide what x is, but it's just for all x. So that's cool. I didn't know what x cubed plus x squared minus x minus 1 divided by x squared plus 2x plus 1 is. But it simplifies pretty easily. Do you remember this thing? SymPy dot simplify. It doesn't simplify at all. I don't know. Some things simplify and some things don't. I guess I kind of figured that would simplify. Oh wait, maybe we can substitute it for something. No, I don't know enough math to do that. Sometimes you don't want to simplify. You want to factor.
Factoring is so cool because I suck at factoring.
Well, not anymore.
Yeah, not
Like,
anymore.
right, problem solved. So let's do x squared. This is always my favorite, plus 2x, because I remember how to do it, plus 1. You all remember that from like middle school or whenever we had to do this?
Yes.
Boom! It's x plus 1 squared. Oh my gosh, I wonder what happens if I change this to a negative. Oh my gosh. Oh, we never have to think ever again for the rest of our lives.
Mm-hmm.
Yay.
And then when it's
Hey.
because like factors, I could factor when it's like x squared plus whatever, but when it becomes like 6x squared plus. something
Yeah,
like
sure.
that,
You want to put 6x squared in here? Let's go. What do you want?
it's difficult. 6x squared. Oh,
That one doesn't factor.
anyway, I don't know.
Maybe that's interesting. We got a 6 out of it.
But yeah, I don't know how to factor when it's more than.
They're also like, hey, what if we like throw a y in there? Well, if we put a y in every term, we can get the y out. So, like, maybe that's cool. Anyways, you never have to think again. That's what I'm telling you. Okay.
That's lovely.
I know. Thinking, it's the brain experiencing pain. That's what I call it. Right. You can also cancel out fractions if you want to do this. There's the equation. And you can factor that. Factor. Oh, wow, that's simpler. Right. So to make all of these examples, I was like manually doing the algebra to know what to type in. So I really convinced myself of the usefulness of this by making these slides. One time I asked a student to calculate how many numbers it would take to represent Avatar, not the last Airbender, the Way of Water, the other Avatar. Yeah, the blue one. Jake Sully, right? Yeah. And I didn't find this was a particularly easy equation to do mentally. It turns out all you have to do is add 10 plus 9 plus 5 plus 9. But you have to remember that's what you're doing. And then, yeah, so, and this was all like a function of like how big an HD screen is and stuff. So like one of these I think is like frames per second or something, right? And then you can substitute in some value. See, like, oh, that's a number. Cool. I love numbers, right? Shout out numbers. And I will see you on Wednesday when I will teach you calculus.
Oh, are you sure?
It only takes an hour.
That's the C word.
It literally only
We will
takes an
never
hour.
have to use our brains when we do calculus.
You will never have to think again for the rest of your life. I've saved you.
Seriously, if I ever do take calculus, well, I don't think I would.
Because you don't have to. I'm going to teach it to you tomorrow. Tomorrow.
Calculus makes me very angry.
See, let the